Hello everyone, my name is Oddgeir Guðmundsson, and since 2012 I've been working with Danfoss, specializing in district energy systems and building technical installations. Today I'm excited to welcome you to this presentation where we will explore and compare various decarbonization strategies for existing multi-apartment buildings. Before we dive into the topic, let's establish some common ground. To meet our climate goals, decarbonizing our energy systems is essential. Today, we will focus on the building sector, which is responsible for nearly 30% of the global energy demand. In the EU, this year is even higher, at around 42%, focusing on EU space heating and hot water account for 79% of the building energy demand. In Germany, they account for 83% of the energy demand. Unfortunately, most of this demand is still met by fossil fuels, with over 50% across the EU and above 65% in Germany. Decarbonizing buildings is a low-hanging fruit because space heating requires low-quality energy, and yet we are currently meeting this demand with high-quality fossil fuels. And decarbonizing new buildings, that's actually straightforward. We should simply prohibit fossil fuels for heating demands. However, for existing buildings, the solution is more complex and depends on factors like insulation levels, existing heating systems, planned renovations, and availability of local renewable energy sources. The ideal way to decarbonize building heating demands would be to connect them to district heating systems. But where district heating isn't available, local electrification is the main alternative. This electrification should strive to meet criteria such as lowest societal cost while remaining cost-effective for owners and end users. It should be reliable and resilient. It should put minimal strain on the power grid, yet to be flexible, to be able to adapt and support the future energy system. This analysis compares the economics of maintaining an existing hydronic system versus replacing it with a new air-to-air system in each apartment. In the analysis, we assume that the phased-out fossil fuel boilers are condensing boilers and that the building has undergone or will undergo light energy renovations, such as new low-energy windows, increased roof insulation, and increased wall insulation. These light renovations are assumed because they typically make existing heating system low temperature ready, an essential step for sustainable and energy efficient decarbonization. This brings us to the electrification options, which are air-to-water heat pumps, air-to-air heat pumps, and direct electrification. When it comes to space heating, the direct electrification can be disqualified as it would lead to a significant and unsustainable strain on the electricity system. In that sense, the applicable alternatives become air-to-water heat pump for both space heating and domestic hot water, air-to-air heat pump for space heating, and air-to-water heat pump for domestic hot water. And the third one, air-to-air heat pump for space heating and direct electrical boiler for domestic hot water purposes. The analysis is based on an average or even a small multi-apartment building. And the considered building is 3-floor high and has a total of 12 flats, where each flat consists of 3 bedrooms, living room, kitchen, and a toilet. The heat demand per flat is set at 9 megawatt hours per year, and thereof the space heating accounts for 7 megawatt hours, and the domestic hot water demand for the remaining 2 megawatt hours. In existing buildings, there are three common heat distribution systems. The first one is a basement boiler with a 5-pipe vertical hydronic system. The second one is a basement boiler with a 5-pipe horizontal hydronic system. And the third one is an apartment boiler with a horizontal hydronic system within the apartment. We will use these three building installation systems designs to compare 4 hydronic-based basement air-to-water heat pump cases with 2 apartment air-to-air heat pump cases. Now, let's explore the cases that we are looking into. And case 1 involves a 5-pipe vertical system where a central heat generation unit supplies both space heating and domestic hot water via vertical risers. A space heating and hot water risers consisting of supply and return pipes then run vertically through the apartment, connecting radiators and hot water taps along the way. Now, with 4 apartments per floor and 6 radiators in each apartment, the building will typically operate 24 space heating risers. And with 2 hot water outlets per flat, there will be additional 8 hot water risers in the building. Now, in case 2, that involves a 5-pipe horizontal system where a central heat generation unit supplies heat for space heating and domestic hot water through vertical risers that go up the staircases and then horizontally into the apartments. Compared to the 5-pipe vertical system, this reduces the number of risers from 32 to just 4 risers. And case 3 explores when converting an existing 5-pipe horizontal system to a 3-pipe horizontal system. This change has some implications. For example, a flat station is needed at the apartment entrances to adjust the space heating supply temperature as well as to prepare domestic hot water. 2 of the existing riser pipes are then discontinued, and this will reduce the distribution heat loss in the building. And the downside is that the central heat pump performance becomes slightly lower due to higher operating temperatures. And in case 4, we are examining a scenario where each flat had operated its own gas boiler. In this case, the gas boilers are replaced by flat stations and a new 3-pipe building distribution system is installed. Cases 5 and 6 are then involving that we simply abandon the existing hydronic system and install a new apartment-based multi-split air-to-air heat pump system for the space heating. And the multi-split system that includes an outdoor unit at each flat and refrigerant distribution and then multiple fan coil units in the flat. In case 5, the domestic hot water is prepared by an air-to-water heat pump, while in case 6, it's prepared by an electrical boiler. When comparing the economics of the cases, we considered investment costs, maintenance costs, technical lifetimes, as well as expected efficiencies of the solutions. In cases 1 to 3, it is assumed that the existing hydronic distribution system can be reused with no need for new pipe investments, but the maintenance costs are still included. And in case 3, it's also accounting for the new flat station that requires then new investments. Case 4 includes the cost of new building distribution system and flat station in each flat. For cases 5 and 6, well, it includes the cost of the new installation. But the one-time cost of removing old installation, such as then the pipes and the radiators, are excluded in the analysis. And this is because of the wide variability in the costs of removing it, as well as the potential for additional expenses related to some cosmetic repairs. Now that we have established a clear understanding of the different cases, we can review the economic analysis results. The results are presented in three ways. The initial investment cost, which is often the top priority for building owners as well as building developers. The annual operating cost, which is generally the most important for the end user. And the annual levelized cost of heating, which reflects the true cost, accounting for initial investments, operating costs, component lifetimes, and eventual future reinvestments. For initial investment costs, then reusing the existing installation is clearly the most effective solution. While new apartment-based systems are significantly more expensive. And the key difference between cases 5 and 6 is that case 5 assumes that domestic hot water is supplied by an expensive, or let's say more expensive, air-to-water heat pumps compared to the electrical boiler used in case 6. Now, focusing solely on the annual operating costs, which represents the end user perspective, can lead to a different conclusion. With this perspective, case 5, using an air-to-air multi-split heat pump for space heating and air-to-water heat pump for hot water, is estimated to be marginally cheaper than the hydronic-based alternatives. However, it's important to note that this doesn't reflect the true cost of heating, as it ignores the required equipment investments. The final perspective is the societal cost or levelized cost of heating, which considers both investments and operational costs over the equipment's lifetime. From this perspective, maintaining existing hydronic installation is more economically favorable than investing in a new heating solutions. And having concluded that maintaining hydronic installation is economically beneficial compared to switching to new air-to-air systems, I would like to highlight a few additional advantages of hydronic systems when it comes to decarbonizing our energy supply. First, the water mass in the hydronic systems enhances the building's short-term load shifting potential and gives options to offer load balancing services to the power grid than on a building level, which generally reduces the complexity compared to end-user operated alternatives. Second, air-to-water heat pumps are already compatible with low global warming potential refrigerants, and this is important as upcoming regulations will make multi-split air-to-air heat pumps solutions more costly. Third, central heat pumps have lower refrigerant volumes and having lower refrigerant leakage rates as well. And they are also easier to maintain than apartment-based air-to-air heat pump systems. And the fourth, outdoor units of central heat pumps can be discreetly placed to minimize noise and preserve building architecture. The fifth, hydronic systems can be connected to future renewable district heating systems, which is a great benefit. In summary, hydronic systems not only provide economic benefits, but also ensure that the buildings are future-proof. If you have any questions, feel free to reach out to me. And with this, I thank you for attending this presentation on comparing hydronic-based heating with air-based alternatives.